Awesome. Well, thanks for the introduction, Jay. We're excited to be here, virtual or in person. Just always happy to be part of the altE event every year. I think this is my fourth or fifth year here, fourth year on this conference. So always exciting. Today we're going to be doing one of our standard modules that's for NABCEP CEU credits. This is the part of our Elite IQ training program. It goes over AC and DC coupling of a PV system and how that relates to the batteries. Kind of going through the different, components, parts, how they interact with the battery, what the differences are, what the advantages are, and kind of just talking through that all. Q&A up at the top, I think Jay mentioned already. Ricky will be around for the presentation, and he'll be able to answer any questions as they come up. And if we have some time at the end, we can always answer questions live as well. We should have some extra time, so we'll hopefully have some good questions we can jump right into. Just thing I wanted to mention, I'm actually going to leave out a lot of the kind of fluff, as I think most people are already kind of familiar with our products. I just want to keep in mind UL certifications. I'm seeing it more and more of a question these days regarding mostly 9540. So I just wanted to remind everybody just right out of the gate that our batteries are 9540 listed with certain configurations. You can actually kind of catch up with our sales team for that info, as well as we've gone through the 9548 testing protocol. If you were at Solar, you might have seen our CEO take my place to present on this as I was out and could not attend. All right, with that being said, let's jump kind of right into the presentation. So again, I'm not going to do a lot of just product overview and talking about our kind of 101 stuff. So if you're not familiar with our products, I would say definitely jump into one of our 101 trainings sometime, and it's a quick overview. Today, we're going to be really kind of diving into these different mechanics of AC and DC coupling, and we will talk about how it relates to the SimpliPhi battery though. So just kind of to jump in as basic definitions, some of the things that might help, and I know this is probably, hey, I already know all this stuff for a lot of installers, and that's okay. For those that don't, I'll kind of give you some basic rundowns here. When we're talking in coupling, at least for this presentation, we're talking about in the context of PV systems. So how is the solar panel, or how the solar panels are coupled to a battery relative to charging? That is really what we're talking about in this presentation, coupling. Now, AC coupling AC power from inverted PV array to be converted into DC power for battery charging. We'll talk a little bit more, or a lot more, I should say, about the mechanics of that as we go through. DC coupling DC power from the PV array with charging regulation in order to charge a battery bank before being inverted to AC power. Cover loads and things like that. All right. So we're going to start with DC coupling and kind of go through a few things there, and then jump into AC coupling, and then kind of bring it all back to the different types of projects and things that it makes sense in. Okay, so DC coupling, DC power from the generation source to the batteries. It's a little bit more direct than when we're talking AC coupling. We're typically using charge controllers. I would say pretty much all the time we're using a charge controller, whether that's an MPPT or it's not. And we're using other types of charge controllers, which we'll talk about, PWMs as well during this presentation. But we're using charge controllers. We're controlling the DC power, voltage and amperage for actually charging the battery. So from that generation source. PV arrangement considerations, we have to think about shading sometimes when it comes to DC coupled, and we'll talk about that as kind of what's new in the market and why that really isn't so much of a factor anymore. But we should always keep in mind also, when we're looking at sizing PV based in a DC coupled system, some of the hangups sometimes are the VOC, the string voltage based on the VOC and ISC, MP and IMP, just looking at how that matches up with a charge controller. And again, I kind of want to emphasize that by saying that we're seeing the market kind of grow towards these being less restricting when it comes to DC coupled systems and larger string sizing allowed. But, for some of the smaller charge controllers, that still is definitely something to consider as the installer when you're doing system design. The AC is just supplied from the inverter. So, we have the DC going to the battery, and then the battery is being inverted into AC for the loads. So, charge controllers. What does a charge controller do? And, this is surface level as could be. I'm not a charge controller manufacturer. I'm sure you will be attending some presentations by some of those this week, and they might be a little bit more in depth and explaining as far as what a charge controller does. But surface level, for this presentation, what we're looking at is it regulates DC voltage and current going to the battery bank to its specific set points and battery limitations for charging from that DC source. Mostly PV, but tons of different other sources as well we can use. And the big ones, wind and hydro, when it comes to charge controllers, still, those are pretty basic DC sources that we might be using a charge controller with to charge a battery. So we talked about MPPT, maximum power point tracking, versus PWM, pulse width modulation. Just kind of very surface level. Again, I don't necessarily have too much of a preference. I always try to say MPPT when it comes to lithium batteries, but I have heard from certain manufacturers that PWM works just fine with lithium as well. So I just typically kind of leave it up to the charge controller manufacturer to decide how their charge controllers interact. But just looking at what it is, the MPPT detects solar panel output voltage in real time. So the system can charge the battery with max power. MPPT constantly tracks any changes in the IV curve, up to 99% efficient. So now let's look a little bit at the PWM, pulse width modulation, modifies pulse width to appropriately charge battery, reduces the width of the pulse to reduce power, often uses FETs to pulse, less efficient than MPPT in most conditions. It's a good fit for smaller PV systems, but again, I think it's pretty rare even that you come across too many PWMs at this point. They definitely are still sold and manufactured, but MPPT is definitely, if you're dealing with like all-in-one inverter charge controllers, those almost always are going to be an MPPT charge controller. Okay, so here's a little kind of pop out of a DC coupled system. I think this one's actually interesting, as you're going to see these, and right out of the gate, I think most people's head goes, that is a micro inverter. If you're not looking closely, that is not a micro inverter. That is a TIGO unit. So this could be either a rapid shutdown unit, where you can see there's an initiation switch here, or even more to our point, could be DC optimizers, which, we talked about panel shading being one of the big hangups of DC coupled systems. Well, optimizers are really easy. They're really, easy to install, easy to collect. They're not that expensive, and they can be connected within line of your PV system in the DC coupled system into the MPPT charge controller. So in this case, we're looking at the Solarc, which, as I mentioned, some inverter, might have that built-in MPPT. In this case, it has the MPPT built right into the inverter. So the charge controller is in this inverter. So we basically take DC power. It's a bit misleading in this because there is a DC bus here, but really we would want to say that the DC power is all being bused to the battery, charging the battery, and then going. So either, if there's excess, it'll go right to being inverted to your sub panel, to your main loads panel, and even out to your grid to sell. If you have excess, but also charging the battery. So that's kind of just a very surface level breakdown of the DC coupled system. So when we talk about DC coupled, we might be talking about what lands on the DC bus. So this is, I want to kind of pull it apart a little bit more and understand here, what that DC bus is. You can see like the most basic rudimentary DC bus right here, just copper insulation and just these lugs to land things on, these different points of connection. So we can see solar coming in. This is an MPPT charge controller right here for Victron. So I say the most interesting designs I've ever seen always are, like a really old school design where somebody might have solar panels connected straight to a battery bank then to the inverter. Then the battery goes to the inverter. Big no-no, don't do that. It's never a good time. This makes a lot more sense. We can see where the connection, so the MPPT actually connected that common DC bus with the batteries connected, with the inverter connected. Everything plays nicely, path of least resistance here. Excess going right to the inverter to be inverted for loads, for grid, whatever it may be, as well as going straight to the battery and the battery being able to pull, or excuse me, the inverter being able to pull the battery here. Okay. So again, very surface level on that as far as a DC coupling, but we'll go even more granular after we kind of get through these kind of basic designs. Let's go into AC coupling now. So AC coupling in a very surface level, we're talking about AC power coming off the roof. So typically it's a micro or string inverter, a PV inverter that is, taking that solar energy that's being produced, and either whether it's on the roof or whether maybe it's a string inverter that's on the side of the house or whatever, maybe even inside, it's the PV is coming and it is actually being inverted right away to AC. So when we put a battery in line, we have to think about how we can charge that battery again from the DC. Since the PV is already being put to AC, we basically, batteries charged to the internal charger of the battery base inverter. So this charger basically converts the AC to DC. So we already have AC coming from the roof or from wherever that charge controller, or excuse me, that grid tied inverter lives. And we just need to convert it back into DC so we can charge the battery. Big one here, PV considerations. We'll talk a lot more about like why, where, when, kind of when it comes to these different systems, but something to think about. PV arrangement considerations is probably the biggest reason I see people go with AC coupled when they're building a brand new system with the battery. Retrofit, whole different game. We'll talk about that later. But you can have larger strings because most of these grid tied inverters, whether it's micro inverters, you got like an N-phase system that has a ton of room to do big strings, or even string inverters that can do large strings. This one you can actually see is kind of a fun little one here. This is Fronius here, and Selectronic, actually the Australian made inverter here. So this is the battery based inverter, and here are the grid tied PV inverters. We're still supplying AC from the inverter. So, when we take that AC and maybe we need some of it to actually go to the battery to be converted to DC, we can still pull from the battery and invert it to AC. And excess can just pass through. All right. So battery-based inverter charging and AC coupling, using the inverter's built-into charger to charge the batteries, as I mentioned. So different from the MPPT. The Solarc's a great example here because we have the whole unit, which has an MPPT in it, but it also has that internal charger. And the charger is really for AC sources, not for DC sources. So it's similar to a charge controller in how it functions, how it charges, the different parameters that can be set in it, but it is typically pulling an AC source, whether that's grid, generator, or in our case, AC coupled PV. So that's kind of the rundown there. And then like we can see here, this is actually the Solarc access unit, which has the Solarc unit in it with the batteries. This unit's cool because it can be DC or it can be AC coupled because it has both those units in. So whether you're using the built-in charger for AC coupling or using the charge controller for a DC coupled system. Frequency shifting, and I am going to just emphasize this by saying I'm not an expert when it comes to this stuff. So I'm just kind of going I keep saying the word surface level, but for frequency shifting, really, this is just what the mechanic is and how it relates to us. But frequency shifting is a mechanism used in a battery-based inverter to regulate or control a grid-tied PV inverter, or excuse me, PV inverter's output. So basically how much it's being, how much it's putting out to the battery, how it's doing it, but also looking at how it turns on those PV inverters. When I say regulates the output, it also regulates if it's on or if it's off, which, if you're familiar with grid tied PV, grid goes down, no more power. Not fun for anybody. You know, I think a lot of customers oftentimes say, hey, why don't I have power when my grid goes down and I have a PV array? Well, we need that battery-based inverter in line to really make that happen. Through frequency shifting, a lot of the time, controlling AC frequency to regulate the charge. So again, you know, it's controlling those PV array or PV inverters to kind of both control how much it's charging, but also being on and off. Some considerations there: frequency profile and inverter age factors. This is super important, I think, still when it comes to AC coupling a system. So if you've got a really old system, you should always take into consideration how old are those grid-tied inverters, what is their frequency range, and how does that relate to the battery-based inverter that I am putting in. That can be a handful for some people. So I always just say reach out to, you know, us if you're putting in a battery, or, you know, reach out to the grid battery-based inverter manufacturer, or even sometimes the grid, the grid-tied manufacturer, the grid-tied inverter manufacturer. They often know. Like I know Enphase, you can call on them for the most part, and they'll explain, you know, you got M250s. Well, here's the range. They, you know, they might need a little extra adjustments to work in an AC coupled way. So that's kind of always a good write-off checklist before doing these AC coupled systems. So here we have our basic grid-tied PV system. You know, these are microinverters. We can see some Enphase here. Basically just, you know, PV panels, inverter, maybe you've got a sub panel, but most likely just like an AC combiner. Your main panel, the grid. So we're just feeding loads on the way out and then excess going right out to the grid. So when we want AC coupled, we're going to use a Schneider here in this example. We basically just throw the inverter, not to make it a bit brash sounding, but we put the inverter nice and in line right here. So let's say this is the sub panel. Now we have a sub panel upstream. This could also be in parallel with this line here, but the way I've always been kind of taught, and I know this is changing slowly, but just throw it in line. So you have your PV going through the sub panel. Now this is a bidirectional port that you might land on, an AC port, because you still have AC coming in, and that is being converted to DC to charge the battery from the inverter's charger. Now it can invert back to here and out to the grid, as well as this can pass through to cover these loads in the grid during normal operation. Or when the grid goes down, ATS kicks in, automatic transfer switch. Now we can power the critical loads while not risking feeding to the grid when the power's out. We can also still produce PV, we can still charge the batteries. So, you know, the benefits of actually adding in a battery-based inverter go well beyond just using a battery in an AC coupled situation. There's, you know, we can use the battery, but we can also self-generate, which is a big deal when it comes to long power outages. Okay, let me see how we're doing on time. Awesome, doing well. So I think we'll have plenty of time for some Q&A. So don't forget, if you have any questions, there is that Q&A block up at the top that you can just type questions right into. Application wise, we're going to kind of talk through it. Some of this might be biased, my own opinion, so just take that with a grain of salt if it is. So DC coupling off grid, you know, we're looking at understanding. Well, let's talk about the flow charge. I guess that's a little out of sync here, this point. But you know, as far as DC coupling goes, when we're talking about application, off grid is really, we want to be DC coupled, is my point. We want to be DC coupled when we're off grid. There's very few situations where you want to be AC coupled off grid. It just doesn't make a ton of sense. And I'll talk about some that does make sense for, but you know, residential scale, want to be DC coupled. The only time I can really think of residential scale being AC coupled is the Sunny Island, because it does have its own Sunny Boy that is really designed for off grid as well, that is AC coupled. So, you know, when we're talking about off grid, we really want to go, you know, understanding how we set everything up there. There's a float charge too that's kind of important. I'll just touch on this briefly. If you ever taken maybe my charge and discharge training, where we talk about the characteristics of batteries and the parameters and everything, you know, we don't really use float for inverter charger. but we do use it for a charge controller and definitely want to use it in an off-grid situation. If you're using PV, float the battery. There's no reason not to. It's not going to hurt the battery. The power is, that you're generating is basically free at that point. Let's let that PV run as much as possible in the day so that your battery is as charged as possible going into the night. So in a DC coupled situation with a charge controller hooked up to like PV or even maybe wind or something like that, float is totally okay. We don't use float when it comes from an AC source, as that tends to be wasteful, whether it's like a generator or the grid, or AC coupled, which we'll talk about the reason why, which is actually a different reason why. So I won't hang up too much there, a little tangent, but battery backup, definitely can use a DC coupled and battery backup. I think there's a slight misconception still coming, from the market. It's definitely gotten better, where people truly don't think that DC coupled is for battery backup grid tied systems. They think that it is for off grid only. It's not the case. I actually say it's a little more efficient for backup systems as well. It's a little more seamless, smooth. The transition when the grid goes down is not as clicky and you don't have to wait as long. It's all just kind of doing its own thing. So, when it comes to island mode, when the grid goes down, it is a lot smoother. You are still charging using the PV during grid outages. And actually things like time of use settings, cell setting, first of all, you can absolutely use in a DC coupled situation with grid tied battery backup. TOU, time of use, is actually a lot more seamless when it comes to DC coupled and grid tied systems, as well as peak load shaving. So I'll kind of talk about, again, I'm talking about applications here, but I'm going to kind of get a little bit more in the coming slides into like why this one versus that one, at least on my opinion, and kind of talk through it. But these are important to keep in mind when we go into that. Large scale CNI, we can definitely use DC coupled system, large DC to DC converters, medium scale built-in MPPTs on a lot of these larger inverters, like the Dynapowers and stuff, and even larger scale MPPTs these days. Probably need a lot of DC optimizers when it comes to those huge systems for doing commercial. But DC coupled, when we're talking about a huge large battery, utilizing an MPPT is never a bad idea. AC coupling, again, I'm just going to say, like grid, if it's off grid, I don't recommend it. It's definitely not my recommendation to go AC coupled off grid. I've seen people do it with inverters that say maybe you can do it, maybe you can't, and it didn't turn out well. So just DC coupled if it's off grid, unless it's large scale, which we'll talk about later. Battery backup, definitely huge when it comes to AC coupled. We're talking about using the existing PV. The retrofit is key. If your PV is already in and it's grid tied, AC coupled is the way to go. It's just hands down. You're not going to redo the entire wiring DC coupled. You might if you're really optimistic or a go-getter, but for the most part, if it's already in place, just getting that battery in line, as we showed during that diagram, makes things a lot easier. Retrofit. In a grid down situation, as I mentioned, we can charge. We can actually charge the PV charge the battery from the existing PV, and we can actually bring that back online. Large scale CNI, definitely I see a lot of, I see a lot of AC coupled situations during large scale CNI. If we're talking about huge solar farms, maybe they are, large scale grid tied farms that are adding a battery. Maybe it is a retrofit onto a CNI project. I see that oftentimes as well. It is important to note use case limitations sometimes. I mentioned time of use and peak shaving already. Well, the reality is a lot of inverters these days are becoming able to use time of use, TOU being one of the biggest applications in residential these days when it comes to areas that have that restriction, that time of use being charged more during certain times. AC coupling typically is not as smooth when it comes to time of use. We're typically using grid use timers versus true reactive time of use. And the reason for that mostly is that self-consumption is not necessarily the same. Self-consumption, meaning, we're we're directly using the battery when we want to versus just not using the grid. That is the difference when an AC coupled system. Typically, the grid needs to go down for that battery to start discharging onto that panel. Whereas a DC coupled system, we can kind of directly say, hey, use the battery for this, because the loads panel is not in that line of the PV array. And I know that's kind of a lot to say without diagrams and everything, but it's just kind of important to note the limitation itself. So if you have a customer that says, I really want to do time of use, they're retrofitting, AC coupled, I would look into exactly what that means as far as the specific inverter you're using. It might not mean true time of use. It might just mean don't use grid from 4 to 6, which does work as well for time of use, just not exactly right. And there's a little more flickering, I've noticed. All right, applications, retrofit versus new system and PV considerations. I kind of already touched on it, but we'll kind of bring it all full circle here. With existing PV and AC coupling, challenges with DC coupling existing PV arrays, as we kind of talked about, is like rewiring. It's actually taking a lot of what's already been done and rewiring. If we want to go from a grid tied system to a DC coupled battery based system, it's a lot of rewiring. We're pulling micros off or pulling string or rearranging strings. I actually would say if it's a string inverter and there's that actually might be easier than if it's in micro inverters. It's gonna be a lot of work to get it reconfigured. And if you're using a low voltage charge controller, then it's a ton of work, as the string sizing is not going to be the same. We might be talking about 3 panels in a string versus 16 or whatever it was in the original system. I already mentioned the misconceptions of DC coupling, grid tied systems. I think a lot of this is derived from the retrofit challenges. That's where this comes from. So in that case, yeah, if you are retrofitting, it doesn't make a lot of sense to go DC coupled. You probably want to go AC coupled, but oftentimes if you're starting from scratch, so a customer comes to you and they say, hey, I want battery, I want solar, I want the whole thing right away. It's a great opportunity to kind of say, okay, let's go DC coupled right out of the gate, especially with these new charge controllers that maybe have higher voltage ranges where you can run larger strings, maybe not as large as some of the grid tied inverters, but still, 10, 11 panels, whatever it may be. And just go DC coupled right out of the gate. It's going to be more efficient. They're going to have a lot more features they can use. And, you might even be saving a component. If you're looking at something like the solar, because I mentioned has that MPPT built in, now you don't need a grid tied inverter and you don't need a separate MPPT charge controller. It's just one in and that's it. So that's the way I would go. I'll probably botch this up, and I don't know the jurisdiction, the laws in every area, but my understanding from our sales team though is that you actually can also apply the ITC credit to the entire system, including the battery, if everything goes in at once, and you can prove X amount of generation from the PV to the battery. So that's a big benefit too, I think, when we're looking at cost savings. We can also talk about efficiency of the PV, AC versus DC coupled. It's not huge, I'm gonna be honest with you. It's just not that large, but you do have to think there's kind of an extra step when it comes to, going from AC to DC back to AC versus just that DC to AC. So there is definitely a difference, but it's close to the same, especially when the inverter might be that chokehold point where it actually is being the efficiency chokehold. All right, we're flying through this. I think we're doing pretty well in time. Awesome. Let's talk a little bit about rapid shutdown. I won't go too deep into this, as my very favorite disclaimer always, local jurisdictions just changes, it always changes. NEC code might be different in your jurisdiction than a different jurisdiction, excuse me. And that being said, your HJ might take the code a little differently than others. So you can never take this on just end all, but we're talking kind of generalities here. So when we're talking about DC coupled RS, oftentimes we might just be talking about a shutoff box if we have just a ground mounted system. So a lot of off-grid systems tend to be ground mounted, I've noticed, and you might just need a simple shutoff box going into the home. You might need module level shutdown. Definitely if it's a residential grid tied and you're in that NEC code, you might need something like module PV level shutdown. Super easy on a DC coupled system. You know, if we have DC optimizers, we can oftentimes, like the Tigo ones, they can be doubled down to be rapid shutdown and DC optimizers. But they also just sell RS only. There's just rapid shutdown attachments. They're pretty cheap actually, and they fit the need to get it up to code there. We might need a remote trip breaker. This is something we're seeing more and more of. I mean, I don't see it a ton in jurisdictions, but I'm definitely seeing it more of, needing that either the inverter to disconnect from that initiation switch on the RS compliance, or needing the actual battery to disconnect, which we can do through a remote trip breaker. But there's some things on the horizon, hopefully that'll make that even easier as the code kind of catches up to everybody. But really single button shutdown, like on our SolarArc Access, single button shutdown. We'll go into a diagram in the next episode, or the next slide, where I'll show you a little bit more of that. AC coupled systems, when it comes to rapid shutdown, again, local jurisdictions might have everything a little different, but really we're talking about microinverter and module level shutdown. Super simple. I mean, it's already built into most micro inverters and even some string inverters. If I'd say most string inverters as well have that panel level shutdown built in at this point, if they're new enough. So that's already kind of built in. Adding the system, the battery-based system in line, doesn't necessarily mess with that RS compliance. If you do have an AHJ that says, I expect battery level shutdown or inverter level shutdown, battery-based inverter level shutdown, you might require a little bit extra components there to be able to set it all up on a single switch. But for the most part, what I see is you put the battery in line, doesn't mess with the RS compliance at all. So here's kind of an example. We've already looked at this example before with the transmitter here and everything, the dongle. And here we see a switch though. This is as basic as we could talk about. If it's like in this situation where this switch will control the actual breaker to the battery, the inverter, and the rapid shutdown components. This is a DC coupled system, and we have all rapid shutdown attached to that single button. All right, and now we go into AC coupled. And again, you already maybe have that PV switch, that single, hey, I disconnect here and everything shuts down. That might suffice for the most part. And what I see for the majority of systems is that does suffice still. Definitely if it's a retrofit where you're not going through as much permitting and things like that, this is where I see it makes sense. However, if a inspector is asking for that battery level shutdown, you might need to reconfigure a little bit to be a little bit more similar to this with that single point shutdown. All right, so we're going to kind of wrap up here with some system design considerations, which I think we've already kind of talked through all together. I just want to kind of bring it all back around here. So we're looking at kind of DC versus AC coupled and like a side-by-side comparison here. And for the most part, what that comes down to is considerations on the system design and PV considerations. So, when we're talking about DC coupled systems, we're limiting the amp to the charge controller. We tend to have smaller strings, and we might even need a PV combiner box that's something a little different than you might use for an AC combiner in a grid tied system. So you might have a little bit more wire runs. But, as far as when the grid goes down, you have a little bit more leeway there as far as, using everything on that critical loads panel without that blip and the charging a little bit more efficiently. Again, charge controllers are definitely becoming larger from what I'm noticing in voltage. So larger strings, easier installation. AC coupled, we're limiting amps through the inverter and internal charger. So some of the stuff we see as far as limitations here, grid down limitations, sizing concerns, which I have a slide kind of at the end there. It'll wrap that up after products. Selling excess to grid versus grid down. So again, that's kind of that self-consumption figure. It's kind of just the pass-through versus the grid being down. We do have larger strings, that's for sure, for the most part. Tends to be less wiring that way as well. We're still going right to the critical loads panel. On a CNI level, when we're looking at DC versus AC couple and PV considerations, we're really talking about large PV systems. So again, optimizers probably going to be key when it comes to DC coupled, DC to DC equipment. And with AC coupled, we're talking large scale string inverters, typically, not mostly micro inverters. So I'd say when it comes to commercial, it's not as big of a deal whether you're AC coupled or DC coupled. It's just more preference at that point, as far as who's doing the install and what they prefer. Okay, I just want to talk a little bit about some products that we kind of talked about, the different things with AC and DC coupling. I want to bring it back to our products, just to kind of talk a little bit about what products make sense in these applications and what they mean. So we look at our PHI battery, our standard. This is our non-comms battery, the 3.8 kilowatt hour battery, both in 24 and 48. However, as you can see here, 48 volts is almost always recommended for AC coupling systems. DC coupling doesn't really matter, but for the most part, the inverters that are AC coupled compatible are 48 volt inverters. But this battery doesn't care if it's DC or it's AC coupled. Definitely if it's 48 volt, just has to do with the inverter at that point. As long as it's connected to an inverter it likes, it doesn't really make too much of a difference to the battery. So again, AC to DC to AC, and then DC to AC when we're talking about the conversions there. But it's still just that battery base inverter. So that makes the big difference, not the battery itself. The AmpliPhi battery is our comms-based battery. It only comes in 48 volts. Again, ability for DC or AC coupled doesn't really make that much of a difference here, as far as the battery's concerned. Currently, the Solar is needed for closed-loop communication. However, we do have the SMA Sunny Island now on that list as well, as I've seen some of those going out. So those are both inverters that we could use for AC coupling, and a communication-based battery. I won't touch on the other things there. It's more of kind of the highlights. I will say one thing, when it comes to AC coupling, we do have some PV limits when it comes to the standard PHI battery. And I'll talk about that in a little bit. With the AmpliPhi, a lot of the comms take out some of that anxiety where it can kind of control its own level of charge rate and things like that automatically. The access unit, we both have the Schneider and the Solarc access unit. For the Solarc, as I mentioned, it's all built in. It's all already connected. The MPPT is in the unit itself. For the Schneider access, the all-in-one, you need to buy it with the additional MPPT in the unit for DC coupling. Comes AC coupled standard. So again, AC coupling with the built-in charger, that's standard. So whether you bought the Schneider or the Solarc, you could do that. I mentioned grid-tied inverter compatibilities. We can always help you out with that. If you're buying our all-in-one unit, we can kind of guide you a little bit more on, hey, this is the grid-tied inverter I have. Is it going to work? We can help kind of guide that conversation, maybe with the correct parties. And then the sizing considerations, which I won't even touch on too much here because I have a slide that kind of shows those considerations and it makes a little bit more sense then. Automatic transfer, if we're talking about our all-in-one system, and really if we're talking about, even just connecting a Solarc with batteries or a Schneider with batteries or an Outback with batteries, whatever it is, that ATS is typically built in automatically. The Solarc does have the advantage of being UPS rated, whereas most inverters do not. The units are outdoor rated, which is kind of perfect for AC coupling because all your other components are outside already. And as I already mentioned, UL 9540, I got to slip that in wherever I can, as I think it's just becoming more and more popular to need that, unfortunately. But fortunately as well, it's a good listing. Okay, so just to kind of wrap up here on this section, I mentioned AC coupled limits. So AC coupled limits being PV limits when you're AC coupling to our batteries. So I'm using the examples of our access here, but it applies to all batteries. Our batteries have a max charge rate of C/2. We recommend that if you are AC coupling, that you match that with your PV. So if you have, for instance, a 3.8 kilowatt hour single battery, which you're never going to probably AC couple, but if you have one single battery, we don't want the PV to exceed 1.9 kilowatts. While the battery-based inverter can ramp up and down the PV array with frequency shifting, I just see it dump too many times. It'll dump the entire PV array into the battery, maybe even just for a split second. So we do recommend following that sizing guide, making sure the battery is twice the size of the PV array. With the AmpliPhi, I will say there's a little bit more give there as it does communicate with the inverter and make sure that that limit's held. So that's a bit different. But with their standard Phi, absolutely. So you can see kind of just some examples here. As if you were to have this Schneider Access with 3 batteries, you want no more than 5.7 kilowatts of PV. With 4 batteries, 6.8 kilowatts of PV. And with the SolarArc 12K, you would want 7.6 kilowatts PV. It's all listed in the manual, but stick to those limits and you definitely won't have any issues. If you need to go above those limits, hey, maybe my PV array is just a little bit too large, just call us and we can talk through it. But we just want to make sure everything's safe and you don't have any issues with your battery. If you're looking for some system design help here, so maybe some tools, some system design help, we've got some great tools that can help with a lot of this stuff I talked about today. Battery sizing, system sizing. So this is a system battery sizing tool. This is a great tool. It actually talks a lot about AC coupling and DC coupling, where it sizes PV and different charge controllers and things like that along with you. We have our lead acid replacement tool. Definitely probably more on the DC coupled side of things, but if you are replacing some lead acid, this helps get through that process of sizing. It also has a quick guide to talk about compatible charge controllers as well. And that helps a lot when you're maybe picking through an old system and putting new batteries into it. We're always available tech support wise and pre-sales wise, 805-640-6700. Manual spec sheets, integration guides can all be found on our website as well. And my last little plug here will be for our Elite IQ installer qualification program. So our distributors, they want this as they want their installers on there as well. More business for you means more business for them, obviously. And for you, you definitely want to be on this if you're an installer. If you've been installing our batteries, this is where you want to land. You end up on our where to buy page, where you are actually seen by customers traveling on our website that actually see you as somebody that's gone through this program. They can trust to install their batteries. Leads tend to go towards these folks as well. It's really a great program to be a part of. It's not for new installers. It's not a requirement to install batteries. If you already have installed their batteries, you should apply for this program. You also get on our newsletter and a few other things, and there's some really big things in the works for this program towards some really cool kind of incentives towards it. So more to come on that, I'm hoping, within the next month here. But again, if you are already installing our batteries, jump onto that link there and you will be able to 10 minutes apply for the program. All right. I think that is everything. I'm going to pop this up so you can see my contact info there. Awesome. And how are we doing on Q&A? Okay. Looks like we have one that was answered, and it looks like we've got 2 lingering here. So if you have any other questions, now is a good time. Type them in. We can always do that right now live or answer afterwards as well if you want to contact us. Correct on the federal credit as long as charging is limited to only charge from solar, not grid. Good to know. So that's a little insight into that ITC credit there from David. Thank you, David. That makes sense to me. So basically, we need to limit it charging from PV. Great way to do that would be a DC coupled system. So again, that kind of matches perfectly. If you want to go get that ITC credit, DC coupled is probably going to be the way to get that done for that charging. Good question. Recycling methods currently available. We work with a lot of recyclers here in the States, as well as some other areas around the world. We can definitely connect anytime you need some sort of recycling through our batteries. There's some second use stuff I'm seeing, but for the most part, the good thing with lithium iron phosphate is we can recycle a lot of these materials and reuse. So depending on where you are, we can pretty much help out when that time comes. All right. Well, it looks like we are just out of questions. Jay, I don't know if you want to hop. Oh, wait, we got one more here. Distance between module and PV limit, wire size. Distance between module and PV limit. I'm not sure. It's a little vague. I might have to see an exact specific example, especially when it comes to wire sizing. It's always going to be based on, the PV itself. So I think I need to probably see a little bit more of
yeah, and if you're working with your altE technical sales rep, they can work with you on wire sizing and distances and all of that. It's not, that doesn't sound like a SimpliPhi specific type question. That's kind of more of a system design type question. They'd be more than happy to help you with anything like that you may be running into.
Awesome. Yeah. I think we're all cleared out here.
All right, very good. Hey, that was a great session, Troy. Thank you very much.
Thank
you guys are awesome. Got some great products there. Fantastic. Oh, another one popped in here. Let's see. Express 7.6 module, want to have PV array.
Yeah, so I would say that's the same question there from the other one. I'd say reach out to either us or your altE rep, and we kind of work through what PV. So what the charge controller is within the Express unit, and exactly how to wire up PV and what the PV limit is on that specific unit based on the spec sheet.
Well, hey, thank you everybody for attending. This was a great session, and look forward to having you available later on, guys. Troy and Ricky, you guys going to be available for questions and answers during the open networking, right?
We sure will.
All right, so we'll have a session there for you, and I'll see everybody then.
All right, thank you, Jay.
Have a great time. Enjoy the rest of your afternoon.